My name is Varun Dutt, and I am a faculty at Indian Institute of Technology, Mandi, Himachal Pradesh, and I am teaching you Large Applications Practicum. This is the part 2 of the first lecture in the course on Make Utility. If you have not seen the first lecture, I strongly encourage you to watch the first lecture where we have looked at what is Make, what is the Make file, how do you run a Make file, how do you create a Make file, and then how do you run Make over a Make file to compile files. We have also seen a tutorial in which we compiled a code where we had to calculate factorial of a program without using the Make utility and then using the Make utility. In this lecture, I'm going to be talking to you about more advanced concepts in the Make utility as we need to make Make more efficient when it runs over large number of files. So let's get started. Basically, as I already told you, Make starts with the first target. Not generally these targets are written on the left hand side of the rules, and only their names do not start with dot. If a target's name starts with dot, it is called a phony target. It doesn't lead to creation of an executable, but it is like something which may allow us to execute a recipe statement. But generally we are talking about targets like routine or hello in the prior lecture, where we actually create an executable by this name. And this is also referred to as the first target, which has the particular target written there, is also called the default goal. In the prior lecture, the default goal was called routine, and we have already seen how we had used the Make utility to actually create a routine target, which is an executable file. So when you run the Make command, Make will first read the Make file in the current directory and then begin by processing the first rule, and then it will go sequentially rule by rule, and it will actually process the entire set of rules in the Make file till it runs out of all the rules. And when it runs out of all the rules, it ends and then it stops execution. So before the Make can fully process the rule or the target routine, it must process the rules or the prerequisites that the routine depends upon. So remember that a rule consists of the target, the prerequisites, and the recipe statements. So in this case, if the Make has to create a target, it first needs to understand the prerequisites. And if there are rules for those prerequisites, then it must process those rules first before it can process the rule for the default goal or the target. So in our example, which we had looked at in the last class, the dependencies are individual source files like those sleep, eat, code.cpp files, and which are independent. Hence, Make simply checks whether they are up to date or not, and we don't need to go and do anything. However, in the case these are .o files or intermediate files or linked files, then the Make may actually search for how to create these files first by looking at the rules which start with the creation of these prerequisites and then execute the rule which uses these prerequisites to create the target. So even if there is a single file is modified, the recipe for the routine is executed, which in turn compiles everything. And therefore, the Make which I showed you in the last lecture is not efficient, because even if we change one file, all the G++ command will execute over all the files and will recompile even those files which had not changed, which is inefficient. So how can we make Make utility more efficient? So one way of doing it is by writing the same Make file which I showed you in the last class in this particular manner, where we are going to actually create a routine. But now, rather than write the CPP files and the G++ statement with those CPP files, I've written .o file, which are intermediate object files created in C++, and written the G++ statement creating routine from the .o files. And in addition to that, for every .o file, we have another rule where we spell out the CPP and the .h header file and the G++ statements for compiling that particular CPP into the .o file. Similarly, we have for main.o, eat.o, code.o, and sleep.o. And you can actually see that in this case, if this is the default target or default goal, the make will first look at the prerequisites and set for the rules where these prerequisites are as targets and run those rules. Particularly check if the timestamp of the .o file here is different from the or the timestamp or the prerequisites for the .o file. In this case, the CPP and the .h file. If there was some change, its timestamp or the time at which the file was saved will be ahead of the .o file. So it will compile only those rules where the CPP file has actually a timestamp which is later than the timestamp of the .o file. In case the CPP file and the .o file have the same timestamp, or the .o file has a timestamp after the CPP file, in that case, those rules will be skipped because there is no change in that CPP file. And therefore, the make will only compile those .o files or those rules in it from top to bottom by looking at those rules where there have been changes in the CPP file, where the timestamp is updated compared to the .o file. And therefore, make will become super efficient and also save time and space. So this is basically what is written in this slide, that if the routine is already up to date, then it will look at the prerequisites, and within the prerequisite, it will look at the CPP file recursively, and it will make those particular rules where the CPP file has changed or has a timestamp ahead of the target file. So the CPP file or any prerequisite file has a timestamp later than the prior created target file's timestamp, then that rule needs to be re-executed. So therefore, the make will compile only those files which are modified, and rest of the files are not compiled again. And then when properly done, this saves time, processor time, and space. So now the question is that how can we make all make more efficient, neat, and more readable? So in this case, we had to write all these .o files in the prerequisite part as well as in the G++ statement, and this will become time consuming. So one way is to reduce time is by creating variables. So you can actually define a variable called object, which has main.o, eat.o, code.o, sleep.o, and then you can define basically a rule which is the same routine rule, and rather than write main.o, eat.o, code.o, sleep.o, we will write $objects in the bracket open bracket close, which basically stands for this. And also in the G++ statement, we can refer to the same $objects. So this is basically variable declaration, definition, and then use of the variables in the prerequisite as well as in the recipe statement to give us the executable. It is very simple, and these rules actually allow us and saves us the time for rewriting these statements again and again. So there is another interesting thing, which is that make has become more intelligent now, and it can also do something called automatic recipe deduction. So in certain cases, we do not need to write recipe statements, and make is intelligent enough to understand how to go from prerequisites to the target without the recipe statement. So for example, it is not necessary to spell out all the recipe statements for compiling in Visual C source files, because make can figure them out. It has an implicit rule for updating a .o file from a correspondingly .c file or a C++ file using a cc command. Same is also true for a CPP file. So basically, when we have to go from a CPP file to a .o file, Nape already knows how to go about it, and therefore you don't need to write prerequisite, you don't need to write the recipes for those rules where prerequisite was the target or what it was getting created. So a more efficient make file with automatic recipe deduction could look like this. Where we have the routine, we have the prerequisite in the first statement, .o, but now you can see that every prerequisite which is having its own rule has only the target and the prerequisite, but it does not contain any recipe. And that is because of the automatic recipe deduction Make will automatically compile the CPP and C files into .o files without writing recipe statements for it. Right now, what we have learned, we have just scratched the surface of what is possible with make. There is a lot to learn further. Remember, I also taught you about phony targets, which have a dot behind their name, like dot routine. Although I did not specifically give you an example of it, but such phony targets can be used to actually execute a number of prerequisite, a number of recipe statements which need to be done. Remember, recipe is a tab statement and it could be any Linux command. It could also mean creating a file, writing some code into the file, compiling this file, and removing this file. So this could be a set of 4 or 5 recipe statements which are defined in a pony rule or in a proper rule, and they get executed when you actually call make look inside a where these rules are written inside a make file. So remember one more thing, that make is not just for C, C++ source file. We can use it for Java files, scripting languages. Generally, anything which can be compiled or run on a dollar prompt could use make. That is kind of a very nice way of thinking about make. Think yourself how you can use make with scripting languages which may not require conventional compiling and linking steps. So you can also think about this. So in industry, it is fairly common for large Linux and Unix programs to include elaborate custom shell scripts which would probe their environment and use information they gathered to construct custom make files. And use of make makes compiling and linking fast and efficient. So in the big projects which you download, which are mostly based on Linux and Unix, generally inside the code, there is a make file which you can run make over. And when you see the make, when you run the make, it will look for that make file. It will open that file. It will try to execute all the rules one by one, trying to create a default goal target by looking at the prerequisite and the rules for those prerequisite. And this can be used across different implementations. As I said, anything we run on the command prompt can be written into a make file and executed through make. So these are the references I used to create the lecture at the new make page and the Colby EDU page. I'm thankful to my TA for creating the slides. And now we will look into another project where in the same activity which we looked into in the first part of the lecture on make. In this case, we need to use the same program, but we need to try out different types of ideas, including first writing the inefficient make file and then writing an efficient make file, which includes variable name, which include automatic recipe reduction, and basically then we want to modify some of the files, like for example you want to modify one of the files or statements in the CPP file, and then we want to run make again and see which files get compiled. Generally, the file which will be changed will be compiled, other files will not be compiled. And you can also put print statements to see how the rules got executed and in what rules were skipped versus what rules actually got executed. So this is basically what is the intent of part 2 activity. So I would encourage you to try out the activity on the command prompt. And again, to tell you, you're using a Windows machine, you may need to install Linux. You can do it from the Microsoft Store, where you need to search for Ubuntu, and you can install 24.04.1 LTS. Here, when you do, you will get an install button, hit it. It might download the file and then install. So this is basically, once you install it, you can launch it by writing Ubuntu, or you can click the shortcut, and when the command prompt open, you need to write explorer.exe dot space dot. So to get where is your path, you can move the activity folder there and then create the make file and start running make. and making Makefile more efficient and rerunning the make. So this ends the part 2 of my lecture on Make utility in the Large Applications Practicum course. In future, we will be looking at other interesting concepts which are relevant for Large Applications Practicum. Thank you.